So let us look instead at something which is much more concrete and informative and indeed ties everything that I said so far together. And this is the case that we are adding up angular momentum from two different objects, and in particular we are going to look at the case that these two objects are two spins. So let us combine the angular momentum of two spins. So the question is essentially, is 2 times 1/2 equal to 1? Well, what we need is to first construct the quantum mechanics of a system of two spins. And what we are going to do is very pragmatic. We're going to say that there are 4 possible states where the first spin is pointing up and the second spin pointing up or down, or the first spin pointing down and again the second spin pointing up or down. And then we consider the most general situation, so we make a state out of this with the following components. And so we can look at this as a 4-component vector. And to give you right away an idea where we are heading, well, let's look at this question mark here. If this would correspond to angular momentum with L equal to 1, then this looks a bit problematic, because for L equal to 1 we would have to have 3 components, but here we have 4. But when we combine two spins, there's no guarantee that they point into the same direction. So here we have some instances where they also point into opposite directions. So maybe sometimes this spin is going to cancel into a state where we don't have any angular momentum at all. And when we combine these two cases, indeed we will obtain the correct answer. But of course we want to do this systematically, and therefore let's turn to the observables of the system. And these are the components of the spin. But now we have 2 spins. So these could be the components of the first spin or the second spin. And we are going to distinguish them by this additional subscript here. Now these should be 4x4 matrices that act on these 4-component vectors, and they can indeed be constructed by very general considerations, but they have a very simple form, so what is going on here is best understood by just writing down the explicit forms. I'm going to start with the x components. Well, the way that I've written them, you see that I left a little bit of space, and that's just to clarify the structure. Because what we see is that these are very nice blocks, where, for instance, here we have an identity matrix, a 2x2 identity matrix, and here we have a 2x2 zero matrix. But then if you squint your eyes in some ways and consider these to be zeros and ones, then this just looks like the normal spin operator for the x component. Now for the second component, we have again a relation to these normal spin operators, but now they appear on the diagonal of the blocks, so in a little bit more direct way indeed. So on the diagonals here we have the Pauli x matrix, and this is then simply multiplied by h power 2. So this matrix here in particular we can then write down also in this very concrete form using just the 2x2 matrices that we have encountered before. And now this also carries over to the other components. So let me first write this down for the second spin. And so that would be our general principle. And then, for instance, just to make this concrete for one of these cases, this is simply this matrix here. And for the first spin, well, there we have to work with these block forms. And what this essentially is that every number in the original matrix is multiplied by an identity matrix. If that number was 0, this just gives us a 2 by 2 0 matrix. If that number was minus I, then it gives us this matrix here. And if it was plus I, then we obtain this one here. And so this is then the Y matrix. And for Z, we obtain this matrix here. And now to see what's really going on, we are going to look at the total angular momentum of the system. I'm going to denote it as J, and this has now 3 components, which are just the sum of the angular momenta of the 2 spins. First, one can verify very directly that this indeed fulfills the correct commutation relations. This can be done, for instance, by multiplying these 4 by 4 matrices. But what is more interesting for us is to simply work out the total angular momentum operator, the one that you obtain by adding the squared components. And this is then the total angular momentum of this composed system, the system made out of 2 spins. And this can now be worked out by just multiplying all these 4 by 4 matrices, and so I'm just going to give you the result. And this result is of the following form. And now this turns out to have 4 eigenvectors, and 3 eigenvectors have the same eigenvalue. Namely the eigenvalue 2h bar squared, and that actually corresponds to L equal to 1, because that's 1 times 1 plus 1 times h bar squared. And then there is one eigenvector which has an eigenvalue that vanishes, and that corresponds to 0 times 1 plus 0 h bar squared, so this corresponds to L equal to 0. So what are these eigenvectors? Well, we have these 3 eigenvectors, which have the first eigenvalue, and then we have this eigenvector, which has the second eigenvalue. And you can simply verify this by doing a matrix times vector multiplication. But what is really interesting at this point is to translate these simply back into our spin states. So we have this state here and this state here, where the spins are definitely pointing into the same direction. And then we have 2 superpositions, where the spins seem to be pointing into opposite directions, but they occur with a different sign. So these are superpositions, where the first one is sort of a constructive superposition, and the other one is a destructive superposition of these 2 possibilities. So this is certainly very nice. Now everything works out in terms of the number of states that we have in our system. So we have these 3 states that correspond to L equal to 1, and this state here that corresponds to L equal to 0. So in 3 cases, angular momentum really adds up as if it is aligned in the same direction. And here we see that very concretely for the plus or minus z direction, while this one here corresponds to something which really adds up into the xy plane. And here we have one case where angular momentum is really cancelling, so it's pointing really into opposite directions, so that the total angular momentum vanishes. So this is really the main message of this little segment, but we can indeed go one step further And for this, we rewrite our state in the basis of the states that we have just defined above. Well, that's not a change for these two basis states here, but then we can introduce some transformed components involving these states here. And in here we have then, for instance, 3 components which correspond to this value L equal to 1. So we could group these indeed into another vector. And when one now checks what happens to these components, when one applies the original 4x4 matrices corresponding to Jx, Jy, and Jz, then acting on these vectors, they just become the 3x3 matrices that we had introduced before for L equal to 1. So we see that there are plenty of relations and analogies between spin and angular momentum. Now that we have these 4x4 matrices, I want to use this opportunity to just very briefly describe how spin arises from a relativistic setting. And with this, we decisively look beyond discourse. What this is really based on is the so-called Dirac equation. And this is the equation that describes the electron and a little bit more in a relativistic setting. Dirac arrived at this equation by starting from another equation known as the Klein-Gordon equation. This is a certain wave equation which has a very clear relativistic structure, and it indeed looks like the equations that we considered in week 1 of this course, when we motivated the Schrödinger equation. And using the operators that we introduced then, it can be written in the following form. Simply written now in 3 spatial dimensions and 1 dimension for time. And we considered the case that we have a particle with a certain mass m. Let me first decode this equation using our earlier definitions of all these operators. This can be brought into the following form. And this is a totally legitimate relativistic wave equation. However, we cannot use it in this form for quantum mechanics. And the problem is this second derivative here. Because we say that the quantum state should encode all the information about the quantum system, including that we should be able to calculate its time evolution by just knowing this state. But here we have a second order differential equation for which we would also need to have the information about the derivative of the state so that we can solve it forward in time. So Dirac set out to write down an equation which is analogous but is a first order differential equation. And the starting point would be to realize that what we have here is really just the operator version of the relation between energy and momentum for a relativistic particle. So the operator version of this relation here. And now it would be tempting to elevate all the symbols here again to operators and let this act on a wave function, but this gives us another problem, because then we would have to expand the square root to make some sense out of this operator, just as we expanded the exponential functions often enough as a power series. But then we obtain derivatives of increasingly higher orders, and this becomes a non-local theory. Dirac achieved something which is much more clever. Namely, he elevated this operator here just to the energy operator. But on the other side, he identified a combination of operators, just a linear combination of the momentum operators that simply squares to the correct result. But for this he needed 4x4 matrices. And this takes the following form. There's this matrix beta, which is multiplied to mc squared. And then there are a set of matrices alpha, which are multiplied to the momentum operator. So the idea is that one can insert this relation down here, and then one recovers the Klein-Gordon equation. But we can also apply this directly to some wave functions, and then we have the so-called Dirac equation. Now, what are these matrices beta and alpha? Well, we obtain the conditions from this feature that we can recover the Klein-Gordon equation. So this gives us some conditions, and then we can find some matrices that fulfill all these conditions. And the most convenient choice is the following, where we first express these matrices in terms of other matrices, which are known as the gamma matrices. And these gamma matrices have a very simple structure, namely a block structure. So these are 4x4 matrices, but made out of blocks, very similar to what we have seen just before. And indeed here we also encounter again the Pauli matrices. So this fixes the Dirac equation in its original form, in the way that it was originally obtained, but with these gamma matrices one can also write it in a relativistic form, where we use the relativistic summation convention, and then it just looks like this. So far this was mainly for information, but now I come to the key point. Namely, considering that these gamma matrices are 4x4 matrices, these wave functions psi here must also have the structure of a 4-component vector. So there are 4 components which are also functions of space and time, but 4 components nonetheless. Psi1, psi2, psi3, and psi4. And now to figure out what the meaning of these components is, we can consider the non-relativistic case, so the case where the momenta are small compared to m times c. And this can indeed be done very systematically by first breaking down this vector into two component vectors, psi plus and psi minus, and then eliminating psi minus from the equations. I'm going to spare you the steps, but then one ends up with a non-relativistic wave equation for psi plus, which has a certain Hamiltonian. And this Hamiltonian is of this form here. So here we have again the Pauli matrices, and here we have the momenta operator, and this is the simplest version of what is known as the Pauli equation. Now, this is the equation that Pauli had written down for the Hamiltonian when he first introduced spin. He indeed wrote it down in a slightly more general form, including the case of a magnetic field, but this is something that we are going to turn to another time. Without the magnetic field, this simply becomes the Schrödinger equation, here just for a free particle. But with the magnetic field, we even learn how the spin is interacting with the magnetic field. But what is more important right here is that this tells us that psi plus has 2 components, and simply one of them is for spin up and the other one is for spin down. So far so good. We have some understanding of 2 of these components, and on top of this we already see that spin seems to have a relativistic origin. But what about the other 2 components? So we understand these 2 here. Well, what we have done here in this approximation, I didn't show you all the details, but there we actually focus on the solutions with a positive energy, while the solutions with this minus subscript will end up to be solutions with a negative energy. This also has a solution, but this is involving a little bit of more insight that we cannot yet develop. We need some other insight of systems with many particles, which is down to Pauli. So let me just tell you the upshot. Dirac developed the picture that there is a whole sea of negative energy states, which are sort of all occupied, which means that there are particles. But sometimes a particle is missing. And so what is really missing and what we are seeing is some missing negative energy, which is like a positive energy. And these so-called holes in the Dirac sea, well, they do not only represent sort of amounts of negative energy which is missing and therefore have a positive energy, but something also goes on with their charge. They actually carry a positive charge, so the opposite of an electron, and then they turn out to be associated with the antiparticle of the electron. So they, at the end, indeed describe the positron. But with this, we really start to set our eyes far beyond this course. To completely understand these aspects, we would now need to resort to quantum field theory. So we better stop here and summarize the elements that are really relevant to us. Well, first of all, we have seen that there are plenty of connections between angular momentum and spin. And we see these, for instance, very clearly when we consider rotations in space. But when we do so, we also see that there are some subtle differences between these quantities. And we have also seen how we can add up angular momentum, in particular when we looked at the example of two spins. And there we saw that the spins can align in two essentially different ways, so that the total angular momentum corresponds to L equal to 1 or to L equal to 0. And this example also gives us an idea of how we can compose quantum systems into larger ones, which will indeed be the subject of a dedicated chapter later on in this course. And finally, we have seen that spin has a relativistic origin, and indeed is naturally embedded into a theory that captures many other fundamental features of elementary particles. And so we should feel much more comfortable to consider it as an intrinsic property of such particles. And this is indeed a lot, and therefore we really stop here.